Section 5.1 is basic concepts of probability. Most statistics students say that this is the toughest section of the course. So just know that before we get started. And we're only going to go over one section tonight. So try to do the homework before you come to class because you know it's going to get more difficult as we go along. Our objectives tonight are to construct sample spaces, compute and interpret probabilities, approximate probabilities using the empirical method, and approximate probabilities by using simulation. We'll discuss each of these, but before we get started, I want to give you some definitions that I used to do first out of the other book. Your book kind of organizes things differently, but I think it'll make tonight's discussion go a little bit smoother if I do this. The first definition is that of theoretical probability. The theoretical probability of an event E is found by using this formula. You read this as the probability of an event E is equal to the number of elements in E divided by the number of elements in the sample space. I'll write that down for you. E is just any generic event, whatever you want to find the probability of. We call it an event, so I'm using E for the variable there. This is read, the probability of event E is the number of elements in event E, that's what the N of E means, divided by the number of elements in the sample space. Well, we don't know what a sample space is, so let me define that for us. The sample space is just the set of all possible outcomes for any event. So for example, if I asked you to find the theoretical probability of tossing a coin and getting a head, my event would be tossing a coin and getting a head. The number of elements in my event is 1 because there's only one head on a coin. The number of elements in my sample space is equal to what? 2 because my sample space consists of both a head and a tail. These curly brackets we use as set notation, so if you're talking about a set of items, we put them in these curly brackets here. This is function notation, like f of x, but now this is p of e. The probability of e is the number of elements in e divided by the number of elements in your sample space. Any questions about the notation or what the symbols mean? So if we were to find the probability of tossing a head, we would say the probability of our event is equal to the number of elements in our event divided by the number of elements in the sample space, and that's equal to 1/2. This is called a theoretical probability. There is another type of probability, and that's called the empirical probability. The empirical probability is based on an experiment. For the empirical probability, the probability of an event would be equal to the number of successes, whatever we're calling a success, divided by the number of trials. So if I wanted to use an empirical probability to find the probability that a coin would land on heads, I would decide how many times I want to flip the coin. That would be my number of trials, and then I would count how many heads I got every time I flipped the coin, and each time I got a head, that would count as a success. So starting with objective 1, we're asked to construct sample spaces. Now you have a basic idea of what a sample space is because we've already discussed that. A probability experiment is one in which we do not know what any individual outcome will be. We do know how a long series of repetitions will come out. For example, if we toss a fair coin, we don't know whether it's going to land on a head or a tail. But if I toss that coin 10,000 times, I know I should get heads half the time, tails half the time. The probability of an event is the proportion of times that that event occurs in the long run. So for a fair coin, that is, one that is equally likely to come up heads as tails, the probability of heads is 1/2, and the probability of tails is 1/2, because over time we expect half of our tosses to be heads, half to be tails. The reason we can expect that is by something called the law of large numbers. The law of large numbers basically says that as the number of trials gets larger and larger, then the empirical probability, the one that we got from doing the coin tosses, will approach the theoretical probability, what we expect just based on the number of elements in our events and the number of elements in the sample space. Here's a graph that represents the results when you toss a coin, and if you toss a coin the first time and it lands on heads, then the probability of getting a head out of that one toss was 1. You got one head out of one coin toss. 1/1 is 1. After 100 tosses, our probability is closer to here. We get 0.49. After 5 tosses, the proportions of head was 0.6. That means that we got 3 heads and 2 tails, so that's a little higher. If we go out to 10,000 tosses, notice how this number starts getting closer and closer to the 1/2 that we expect to get. This red line here represents our theoretical probability. This blue line is the empirical probability after we do so many coin tosses. The number of coin tosses are down here. So let me write in plain English what the law of large numbers means. And I've tried to color code this so that you can tell which graph is blue and which graph is red. The law of large numbers basically says as the number of trials increases, and your number of trials are down here on the bottom, then this blue line, the result from the empirical probability, approaches the red line, which is our theoretical probability. Now we're ready to talk about what a sample space is, even though we've already discussed it a little bit. The collection of all possible outcomes of a probability experiment is called a sample space. I've got 3 situations or 3 scenarios here, and I want you to tell me what the sample space is. Describe the sample space for each of the following experiments. We've already done the first one, the toss of a coin. Our sample space will be 1 head, 1 tail. If you're rolling a die, die is just singular of dice. Dice is more than 1, die is just 1. How many numbers are there on a die? 6. So our sample space would consist of the numbers 1, 2, 3, 4, 5, 6. Our sample space is all of the numbers. If you're selecting a student at random from a list of 10,000 at a large university, what would your sample space be? All 10,000 students. I'm not going to name them, but that's what you would have. If we looked at the number of elements in the sample space, here we would get 2. The number of elements in the sample space here we would get 6. And the number of elements in the sample space here would be 10,000. Let's look at an example that I'm just going to make up. If you're rolling a single die, what's the probability of rolling a 4? 2 is not a probability. Probabilities are numbers between 0 and 1. Let's start with step 1. What is our event? What numbers will be in our event? 5 and 6, because 5 and 6 are the only 2 numbers out of the numbers on a die that are bigger than 5. We've already identified what our sample space is. It's right here on B. How many elements are in our event? Not the sample space. 2. There's just 2 numbers there. And using the formula that I gave you for a theoretical probability, we would say the probability of the event is the number of elements in the event divided by the number of elements in the sample space. So this would be 2 over 6, which reduces to 1/3. So if you're rolling a die and you want to know what's the probability of rolling a number bigger than 4, it would be 1/3. This formula for theoretical probabilities you probably want to put on your notes on your formula sheet. It's important that you go through the same process that I just did. Identify what elements are in your event, then how many elements are in your event. Identify what your sample space is and how many elements are in the sample space. Then you just drop those numbers into this formula. It's pretty straightforward for basic probabilities. Probabilities can get more complicated, and we're going to do those after tonight. So make sure you get caught up on the homework tonight. Now let's talk about what a probability model is. We're often concerned with the occurrences that consist of several outcomes. For example, when rolling a die, we might be interested in the probability of rolling an odd number. Rolling an odd number corresponds to the collection of outcomes consisting of 1, 3, and 5 from the sample space 1, 2, 3, 4, 5, 6. In general, a collection of outcomes of a sample space is called an event, and I've already been calling them that. Once we have the sample space, we need to specify a probability of each event. This is done with a probability model. We use the letter P to denote probabilities. For example, we denote the probability that a tossed coin lands on head by P of heads. In general, if A denotes an event, the probability of an event is denoted by P of A. In your probability model, typically we'll organize information in a table, and we would have our event listed here and then the probability of the event over here. For a probability model, if I had tossing a coin and getting a head, the probability of doing that would be 1/2. The other thing that I could do is get a tail. The probability of that would be 1/2. In order to have a valid probability model, all of these probabilities have to sum to 1. Basically, the probability of your sample space has to be equal to 1, and you can't have negative values. These have to be numbers between 0 and 1. Objective 2 is to compute and interpret probabilities. The probability of an event is always between 0 and 1. In other words, for any event A, the probability of A has to be between 0 and 1. Probabilities are measured on a continuum. If the probability is 0, then that means that it is impossible for that event to occur. If the probability is 1, it's guaranteed certainty that that event is going to occur. And then the closer a probability is to 0, the least likely it is to occur. The closer the probability is to 1, the less likely it is to occur. If I have a probability of 0.5, it's exactly halfway in the middle, then we have no idea what's going to happen. It's 50-50, equally likely chance of it happening or not happening. Probabilities with equally likely outcomes is what I called our theoretical probabilities. And here's the formula written up the way your book likes to write it for a theoretical probability. You take the number of elements that are in your event that you're interested in divided by the number of elements in the sample space. That gives you the probability of your event. For example, in the Georgia Cash 4 lottery, a winning number between 000 and 999 is chosen at random, with all the possible numbers being equally likely. What is the probability that all 4 digits are the same? In words, our event here is that all 4 digits are the same. So I could even list this out as 000, 1111, 2222, all the way down to 9999. How many elements are in this event? How many of these numbers are there? 10. There's 10 numbers. Our sample space consists of all 4-digit numbers from 0 to 9999. How many elements are in our sample space? No, this goes from 0000 to 0001, 0002, 00 all the way up to 9999. 10,000, right, a whole bunch of them. Because we've got from 1 to 9,999 plus the 0 makes it 10,000. Does that make sense? Putting this information together, then, I can find the probability of our event using this formula for theoretical probabilities. It's the number of elements in the event divided by the number of elements in the sample space. For this problem, that would be 10 divided by 10,000, which is 1 over 1,000, and you could probably get by with writing your answer like this, 0.001. Now I want to show you something on your calculator, something that makes the price of the calculator worth it. If you take 10 divided by 10,000 on your calculator, you get 0.001. If I told you to write that answer as a proper fraction, all you got to do is hit math, enter, enter, and it converts that decimal to a proper fraction. Math, enter, enter is cool. For example, if you had, let's say, 40 divided by 258,000. If I ask you to convert this number to a proper fraction, I don't know if it'll do it for this one because the denominator may be too big. It does. It's 1 over 645. As long as the denominator has no more than 4 digits in it, your calculator will reduce that fraction for you and give your answer as a reduced fraction. Because I would rather look at 1 over 645 than this. When you're rounding probabilities, the general rule of thumb is to go to 3 or 4 decimal places. I think your book is going to ask you for 4 more often than not, but if you're writing up a report using APA, I know APA lets you get by with using 3 decimal places. So math, enter, enter is your friend when it comes to converting decimals to reduced fractions. Notice all the probabilities have to be numbers between 0 and 1 as well. This is a very low probability. The probability of winning this lottery is really, really low. It's what we consider an unlikely event, and we'll talk about those in just a minute. Here's another example. It says a family has 3 children, denoting a boy by B and a girl by G. We can denote the genders of these children from oldest to youngest. For example, GBG means the oldest child is a girl, the middle child is a boy, the youngest child is a girl. Without looking at this, let's talk about what our sample space here would be. It's possible that all 3 kids are boys. Then it's also possible to have 2 boys and a girl. That girl could be born last, or middle, or first, or you could have 2 girls and a boy, with the boy being last, middle, or first, or you could have all 3 girls. Looking at this, I have started out with 0 girls. In these next 3, I had 1 girl. In these next 3, I had 2 girls. And in this last one, I had all girls. This is my sample space. It covers every possible outcome. And sometimes when you're making a sample space, you need to make a list like this where you just methodically go through every possible outcome, listing every possible outcome. Until we learn how to count in here, this is pretty much what we're going to be stuck with. And you just thought you knew how to count. I'm going to show you how to count in here later on. Now we've got enough information that we can answer these questions. For part A, we're asked what is the probability that there was exactly 2 girls? So our event is exactly 2 girls. How many ways can I come up with exactly 2 girls? That's the number of elements in my event. Look at our table over here. There's 3 ways I could come up with exactly 2 girls right here. I could have 2 girls and the boy last, or the boy in the middle, or the boy first. That gives me exactly 2 girls. I also need to know the number of elements in my sample space. How many elements are in the sample space? 8. Putting that information together, then I can find the probability of my event. The probability of my event is going to be equal to what over what? 3/8. It's the number of elements in your event divided by the number of elements in the sample space. Part B says what is the probability that all 3 children are the same gender? So now my event is that I have all 3 the same gender. I could actually list these, it wouldn't be so bad. I could have girl, 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 or boy, boy, boy. That's the only way that I could have all 3 kids be the same gender. How many elements are in my event now? 2, and my sample space is still 8. So the probability of this event is 2/8, but that reduces to 1/4. Do you see how if you remember this formula for theoretical probabilities, and before you ever try doing anything, identify what these component pieces are, it makes the problem easier. You see how I write out my event in words or listing things, and then I identify the number of elements in the event and the number of elements in the sample space. That makes calculating the probability easy. Sampling an individual from a population is a probability experiment. The population is the sample space, and the members of the population are equally likely outcomes. In this example, we're told that there are 10,000 families in a certain town categorized as follows. There's 4,753 that own a house, 1,478 that own a condo, 912 people rent a house, and 2,857 people rent an apartment. If you added all these up, you'd see that that's your 10,000 people in your population. Part A says what is the probability that the sampled family owns a house? So on Part A, my event would be that they own a house. How many people own a house? 4,753. How many people are in my sample space? The 10,000 people in the town. So the probability of my event is going to be equal to the number of elements in my event divided by the number of elements in my sample space, and I get 4,753 over 10,000. And odds are they would not want to see this fraction. They wanted to see this written out as a decimal, 0.4753. On Part B, we're asked what is the probability that the sampled family rents? My event in words are people that rent what? What can they rent on this list? A house or an apartment. Because we were just told rent. There's 2 rents up here. You can rent a house or you can rent an apartment. To find the number of elements in my event, I need to add 912 to 2857. And when I do that, what do I get? Now I can put this together and see that the probability that they rent will be equal to the number of renters divided by the number of people in my sample space, and that's going to be 3769 divided by 10,000, or 0.3769. Because I had 2 groups that rented, I needed to add those together to get the number of elements in that event. Now let's talk about unusual events. An unusual event is one that is not likely to happen. In other words, an event whose probability is very, very small. There are no hard and fast rules as to just how small a probability needs to be before an event is considered unusual, but we do use the following rule of thumb. An event whose probability is less than 0.05 is considered to be unusual. This is a threshold that will be used throughout the course, especially when we get into testing hypotheses in Chapter 9, I believe. This is what we use as our cutoff for saying that something is unusual. For example, In a college of 5,000 students, 150 are math majors. A student is selected at random and turns out to be a math major. Is this unusual? Well, the first thing we need to do is find the probability that a randomly selected student is a math major. Our event here is that we select a math major. How many elements are in our event? 150. We're told there's only 150 math majors at this school. What's our sample space? The 5,000 students. Our sample space is all the students at the college. So the probability that we select a math major will be equal to the number of math majors divided by the number of students at the college, and that's going to be 150 divided by 5,000. And we go to our calculators and we look at 150 divided by 5,000 and we get 0.03. Would you say that it's unusual to find somebody at that school that's a math major? Yes. Because this is less than 0.05, B/C is my abbreviation for because. Objective 3 is approximating probabilities using the empirical method. Remember, the empirical method is just when you're doing an experiment. And here we said the probability of an event using the empirical method is the number of successes divided by the number of trials. The law of large numbers says that if we repeat a probability experiment of large number of times, then the proportion of times that a particular outcome occurs is likely to be close to the true probability of the outcome. We've already talked about that. The empirical method consists of repeating an experiment a large number of times and using the proportion of times an outcome occurs to approximate the probability of the outcome. For example, in 2010, there were 2,046,935 boys and 1,952,451 girls born in the U.S. Approximate the probability that a newborn baby is a boy. Here we're calling a boy a success. The number of boys that I have is 2,046,935. Our sample space would be what? Our sample space is all babies born in 2010. How do I find the number of elements in my sample space? Add the boys and girls together. 2,046,935 plus 1,952,451 equals, so the probability that I have a boy is equal to the number of boys divided by the total number of babies born in 2010. When you put that in your calculator, what do you get? Round your answer to 4 decimal places. So that's close to the 50% that we would expect if there's only 2 outcomes, right? It won't calculate it as a proper fraction, but it will give you a decimal. It's got to. Alright, let me type it in and you just kind of follow along and see what happens. Are you on your home screen? Hit second mode. Okay, we got 2,046,935 divided by 3,999,386. Oh yeah, no, you can't put the, whenever you're using your calculator, you can't put the commas in the calculator. It'll freak out. I'm not going to put that in the video. I probably should, but I'm not going to. I'll just make a note. This is an introductory statistics class, not a traditional math class, so I'm assuming that you're probably not very mathy, so I just need to point out that you don't want to use commas when you're typing in the numbers in your calculator. It will give you an error message. Objective 4, approximate probabilities by using simulations. In practice, it can be difficult or impossible to repeat an experiment many times in order to approximate a probability with the empirical method. In some cases, we can use technology to repeat an equivalent virtual experiment many times. Conducting a virtual experiment in this way is called using a simulation. So if I wanted to simulate 1,000 coin tosses, you have 2 options at this point. You can go home and toss a coin 1,000 times and then come back with your hand sore and tell me the results, keeping track of all the heads and tails you get. Or you can use your graphing calculator to do it using something called a random number generator. On the TI-84 Plus calculator, the random int is the command that we use to calculate a list of random integers. How we get to this is we'll hit the math button, which is right underneath the alpha button, go over to probability, and then number 5 is the random integer. I'm just showing you this in case you need it for for some future event. I'm not going to put a question like this on your test where you have to generate a list of random numbers. I just want to show you that it's possible. So for example, if I wanted to simulate rolling a die, my lower bound here would be the first number, the smallest number on a die. The upper bound would be the largest number that's on a die, and then n represents the number of rolls that I want to simulate. So if I want to simulate 100 tosses of a die, I could use 1 for my lower bound, 6 for my upper bound, n is 100, hit paste, and then I want to store these numbers somewhere. And I want to store them in a list, so down here above the on button is the store button, and I want to store these numbers in list 5. It's actually going to pop the list up on my screen on this calculator. Your calculator may not, it may just automatically populate list 5. In order to see the data then, you have to go into list 5 by hitting stat enter, and then here's all the different numbers that my calculator generated for rolling a die, and they're all numbers from 1 to 6. Now the question is this truly random? Because if we all had brand new calculators from the store and never touched anything on them, and we all put in the same constraints, we would all get the same list, the exact same list. So can it really be random? No, it's using a very complex algorithm to generate this list of random digits. Randomness is something that's very difficult to accomplish, true randomness. And what I've just walked you through was the steps for simulating rolling a die 100 times. Here's output from a simulation in Excel. I'm not going to teach you guys how to use Excel or do Excel, but suppose that 3 dice are rolled. The smallest possible total is 3. So if I roll 3 dice and I'm adding the results, the smallest number I could get on each of the dice is 1. And if I add up the total, then I've got a total of 3. The largest number I could roll on any one of the dice is 6, and 6 times 3 is 18. So the largest number that I could roll would be 18. So any number between 3 and 18 is a possibility for rolling a sum or a total whenever I roll 3 dice. Notice if I used this simulation result from Excel, they did a list of 1,000 numbers for dice 1, 2, and 3. Each one of these columns was generated randomly, and then this fourth column they just said let's add up the numbers that we got from our roll. This frequency table then summarizes the results for 1,000 rolls. If I wanted to know what was the probability of rolling a sum of 10 from this simulation, I would go down to my frequency table. I would look and see, well, the roll of 10 occurred 128 out of 1,000 rolls. Well, 128 divided by 1,000 is 0.128. So we would say the probability of rolling 3 dice and getting a total of 10 is 0.128. I want to point something out that's interesting here. In order to roll a 3, you have to get all 3 aces on all 3 dice. That's very hard to do. In order to get an 18, you got to roll all 3 sixes. But in order to get a 10, I could roll a 1, a 4, and a 5. I could roll a 1, a 3, and a 6. I could roll a 1, a 5, and a 5. I could roll a 1, a 5, and a 4. I could roll a 1, a 6, and a 3. You see what's going on? There's a whole bunch of different combinations of numbers on these 3 dice that I could get that add up to 10. That's why that frequency is so much higher. You're more likely to get a 10 when you roll because there's more different combinations of numbers on those 3 dice that would give you a 10. The only way to get a sum of 3 is to roll a 1, 1, 1. The only way to get a sum of 18 is to roll a 6, 6, 6. It's harder to get those combinations. We have fewer counts, which means smaller probabilities. And that wraps up section 5.1. We've discussed the law of large numbers, the definition of probability, sample space, and an event. We've looked at how to compute probabilities with equally likely outcomes. The rule of thumb for determining when an event is unusual is basically if it's less than 0.05. And then we looked at the empirical method and simulations.